It has yelled at you. It is recording. And then I got a screen share. I should make it the screen. Is this the right one? Oh, cool, man. Those little boxes. Can everyone see Definal?
Yes, sir.
All right. So this is the first one. So I have two of them here.
Okay.
Looks like he puts bonuses on these. I don't know if we'll see bonuses. The bonus for this one is nuts, by the way. But even so. Zoom in. Let me do this. Where is there anything else anywhere? Nope. All right, there we go. And let me get this up. Put that over there. All right, now we can see what's going on. So I think we've actually worked one of these before in class, or we worked a similar one. Don't know if it's the same one from the problem, but even so I can almost guarantee we'll see this problem probably slightly changed, that being the memory range problem here.
Yep.
So this is 20-point problem. You can see that calculating the range, this is weighted at 6 points, and there's a bunch of true false. So that's really the whole problem. You can see that a lot of the stuff is just like short answer, quick stuff. So it's not about getting one big problem wrong at this level. It's more about just having the general scatter knowledge to be able to answer all the little ones correctly. Because like even this 20-point problem, it's all broken down, right? There's, from what I can tell, unlike the midterm, there isn't even really like big code writing anywhere. Like it's just like ask you what something does, write like 4 lines to set up a port, like this one kind of thing. But even so this is more of like be on your ball game in general intelligence and understanding, as opposed to having like the ability to just grind out a program in like 30 minutes, which is probably more beneficial to the vast majority of people, because not everyone codes at the same speed, but recollection is relatively quick amongst all individuals. So to begin, this is just standard memory range problem. So it gives you the total address space, helpfully in ranges here. Now, keep in mind, I noted this, and you can see everywhere, its top range is 0x1 FFFF, right? 5 hex digits, but its lower range was denoted with 4 zeros, which was false, and it is still not corrected, and it never will be. So just putting that out there. It's a final from 2012 or something. That's just how it's going to be. All right, so you have to fill in the table, that being this thing at the bottom, with the following information. First 16 bytes is reserved for special functions, blah, blah, blah. Index 240 is reserved for 8-bit, blah, blah, blah. You don't really need to know what it's reserved for. You just need to know how much space is reserved for a particular section.
Yeah.
And then the last thing it'll tell you here, or it's important to understand here, is where does it say? Word or byte? It says byte address right there. The last byte address is, so you can know that this is a byte addressable system. It's a very important distinction. If you say it's word addressable or byte addressable and you're wrong, you will lose all your points, even though you're only going to be a single byte off. You will still lose a lot of points for that, so not worth. But you just want to read the question very carefully and don't assume that it's one or the other. Like in this case, you can see, let's read this whole on phrase for phrase, blah, 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 fill in the table, know the following, bytes of the address space, 8-bit, blah, blah, blah. It never says word anywhere. So basically, if you read through this problem and you don't see the phrase word, assume byte unless explicitly told otherwise. So to begin, special function registers tells you right here, you have 16 bytes reserved for it. Starting bytes. Address is right here, right? So you can just move up. So let me
what you'll do is you'll add 16 and subtract 1
straight up. So if you add 16 to this address, because each address is a byte address. So you, as Sydney said, you add 16 and subtract 1. So what does that realistically mean? Well, in hexadecimal, you can represent 16 distinct values up to 0 to 15. Therefore, 16 minus 1 is 15, F is 15. So your end address here is 0x0000F.
F.
That is all,
there you go.
right? If it were word addressable, it would be E. It'd be down 1 more, because you have an extra byte there, but it would also be 8 words. So it's a whole other thing. But that's just that. So does anyone have any misconceptions or want a more in-depth ways to calculate addresses here? Or can we move on and just speed run these rest?
Speed run the rest, I
All
think.
Right. 8-bit peripheral. You're going to want a calculator for this, by the way.
Yeah, one thing that's nice to have is a calculator that can do hex addition and
That's
subtraction.
stinky. Just convert everything to decimal and convert it back. Easy
You could do that,
peasy.
but it wastes time.
Yeah. Fair, it does, yeah. And actually, most modern calculators have a hexadecimal binary function. You just got to go into the documentation to find it.
Right. And then I think TI offers like a programming special one.
Yeah.
It's like pretty cheap. So
Yeah. All right. So next one is 8-bit peripheral devices with a range of 240 bytes. Now you got to remember the previous, this one doesn't have a starting address of 0x0000 because that was the special function. So its starting address is 1 byte past the previous ending address.
yep.
Which if the ending address was 0x0000f, the next address is the 1 byte past. So you overflow the f, so add 1 to
So you
0
get
is going to be
0.
yeah, it's going to be
Right.
0x00010 for 240. That's your start address. So that's what you'd put right here. And then your end address is you just add 240 to that in the
240
hex
plus that.
and then subtract 1. And then you're just going to end up with that just ends you, funny enough, at FF.
Yeah, at FF. There you go.
And then the next one, you just do the same process. You overflow
100.
1, which as he says is 100 in hex. Then you add 256, subtract 1, which will result in 0x001ff. So it just overflows again.
Mhm.
And then 8 kilobytes here, very important. So 8 kilobytes. You need to
It's
remember what is
1,000
that?
Yeah,
It's
8
1,000.
times 1024 if you like to memorize it in storage block chunks.
Yeah, it's
Um,
not 1,000 bytes. That is not the case. That will
Yeah, it's
get you the wrong answer.
1024.
Yeah.
It's like 2 to the what 10th kilo?
Something like that.
I don't actually know.
I feel like to the 10th. Yeah, it's to the 10th.
Wow.
Yeah. So this one has a given starting address because the previous ending address of the 16-bit peripherals does not actually go up to RAM memory. So he has to give you a new starting address there. So you're given the starting address, so you just have to add 8 kilobytes. So you just calculate the amount of bytes there. So that's going to be 8 times 1024. So that is a big boy number, but not really. So it's just going to be 8 times 124, well, 1024, which will use you 8192. So 8192 bytes. You convert that to hex, you add it to this, subtract 1, and you'll get 0x030ff as your end address for the RAM memory. And then this time you get to use the previous end address as the start address for flash memory once you've added 1. So 0x030ff plus 1 is 0x03100. And then flash memory, as mentioned, or as thing, the last byte address goes up. Flash occupies the rest of the address space, so you can just move on. And it'll go all the way up to the end, which means it goes all the way up to 0x1ffff.
Yep.
And you're done.
One thing to note whenever you're filling out these addresses, your start address will more than likely always have a 0 in the rightmost position. So it'll be an even starting address. And then your end address are typically F's rightmost.
Yeah, every address in the start address in this block had a 0 at the end because just the quirk of the math, every time it overflows to the next section, it resets your lowest bit.
Sets to a 0.
Or your lowest hex digit.
So if you need to sanity check yourself, that's a quick way to do it.
So now you can say, B, what is the size of flash memory in kilobytes in the example above? Well, you can convert the number, the size of the flash memory. So flash starts at 0x03100 and ends at the highest address. So you get the absolute value of that by subtracting the lower from the upper to get the absolute range, the absolute amount of flash. And then you just multiply that. Oh, wait, no. You have to divide it, sorry.
Yeah, divide by 8.
Divide by kilobytes. So,
oh, wait, no, 1024, yeah.
And there you go. So we can do, on my calculator, the quick maths for that is, here, let's just do it funny. Funny mode. So if we do the upper address of flash, which is going to be these Fs, minus the lower address of flash, which is 0x0. 3, 1, 0, 0. There we go. Is there someone echoing?
Whoa.
Oh, Roosevelt, you're echoing. Because there's 2 of you. There we go. I think it's
It's
fixed.
interesting.
All right. So then we just do this math, right? So 0 subtract from F, still going to spit on F. F subtracted by 0, still going to spit on F. F subtracted by 1. Well, actually, no, this works. Yeah. We don't have to do 2's complement here, right?
No, I don't
Pretty sure you
think
can just
so.
subtract it because then F's just what, E? No, that's not E. B, C, D, E, F. No, it is E. E. And then F, E, A, B, C, D, E. That's going to be C.
Yeah, C, and then
1.
C, E, F, F. 1
Yep.
C, E, F, F. Yeah.
Yeah, and then you convert this to, you can convert this to just decimal and divide by 1024. So let me see. Let me do this. There we go. New tab.
Oh.
Speed run. I love how it just sits there. So we do 1 C E F F. Convert, and then you take this, right?
I get like 116. You round up.
He doesn't round up in his.
Oh, does he not?
Rip. Come on, where's my number? It doesn't copy over. I don't think you can copy and paste into calculator. You can't. Fine, we'll do it this way. Yeah, that's the number. And what he writes in his answer solution is 115.75. That's what he writes.
Yeah, what you do is you add 1 to your hex number.
Yeah, because
and then it does that for some reason.
Yeah, that's that. So probably better to do.
So you want it on like an even number.
There we go. So
decimal wise.
I will clear that now. So that's how you do that. You just divide by 1024. I don't want to be doodling anymore. Let me turn that off. There we go. Back here. So that's what that is. Now we'll go. So this, the size is just, you take the start address of your target range. You take your end address minus your start address, convert to decimal, divide by the number it's asking for. In this case, divide by 1024, spits out a value, write it here, 2 points free, right? Now you got some true and false, the move.w, so word move of immediate 34 into this will actually write the constant into flash memory. No, you can't do that. I mean, yeah, you can't. You're not writing stuff into flash during runtime because then you're just going to overwrite your program, and then Milankovic will frown upon you. So next, the program downloaded into flash memory through JTAG port will remain in the flash memory only until the power is turned off. No, that is false. Flash memory is not, what is it? The phrasing I'm looking for is it is not, it's solid state memory. It is not, what am I trying? Come on, phrase. RAM versus flash.
Well, it says until the power is turned on.
Oh no, I know that it's this.
Oh, will be lost when the device is turned off. Yeah, no, that's
this
false.
is false, but I'm trying to remember
because flash. I mean, think about it. Flash drive.
Well, no, but what I'm trying to remember is the there's a word, and it's, we all know this. I'm just,
it's volatile.
Yes, yes, there it is.
SRAM.
Volatile versus non-volatile. So flash memory is non-volatile memory. It'll stay there. RAM, anything else like that is volatile memory. If you don't have power, it will just lose. It'll just erase itself. That's that. And then E is just the opposite question. The content of RAM is lost when the system goes into low power mode. This is false.
Hold on one second.
No, that is false.
Yeah. What's up?
So you said flash memory is non-volatile, so that means that it doesn't know that it is bound to change. While RAM is volatile, so that means it's bound to change. Right?
So if I take a flash chip and an SRAM chip, or just a RAM chip, right? If I put data into the flash chip and then unplug the power, and then I wait 100 years and I plug the flash chip back in, the data will still be sitting there. It's non-volatile. It'll just sit there. It won't go anywhere. Nothing will happen to it. So it's non-volatile, it'll hold it without power. RAM is a volatile memory type. So the second I take power away, the RAM loses its data very, very quickly on the order of, microseconds. And you can't get that stuff back. So the phrasing for that is non-volatile memory means it will hold it for a long time. Think solid state drives, hard drives, anything like that. And SRAM or RAM or DRAM, anything that's random access, right, is a type of volatile memory where it will lose its data very quickly the second you take power away. So then right here it says true or false. So this is kind of like trying to bait you because it's got you into thinking about memory powering and stuff like that. It's going to try and bait you with this question. The content of RAM memory is lost when a system goes into low power mode. No.
Low power mode keeps power to the RAM chip. It just disables CPU clocks.
Yeah, it just turns off clocks and doesn't even turn them all off. There's always, unless you like the deepest possible low power mode. But even so, it would make zero sense for low power mode to turn off your RAM because that's where all your variables are held. So assuming you write programs that use variables like a normal person, if you turn off your RAM, you can't really do anything, can you? Until you turn it back on, you're kind of just frozen.
And this is actually what happens when your Windows computer or Mac computer goes to sleep. It'll it'll keep everything that's in RAM, so all your programs that are running, and basically just keep power to it while it turns off everything else.
Yeah, and then there's also the extra thing you can add in your Windows menu called Hibernate, where it straight turns everything off. But what it does is it'll copy the current RAM as well as current machine state into your like solid state memory, and it'll hold it there.
Yeah, so it doesn't have to power RAM.
So the answer for E is false, right?
You bet. All right, so then F, the content of the general purpose and special purpose registers is preserved while processor is in low power mode. So this is true.
True.
It should not go away yet again. Like if you go into low power mode and the special purpose register, aka like stack pointer, stack pointer,
program counter.
Yeah, program counter, all that stuff.
Global interrupts.
If all that stuff got wiped when you go into low power mode, how the hell are you supposed to get up? Special purpose registers also where interrupts are. So how the hell are you going to wake the thing up, right? You can't. So that is true. You have to preserve that information. And then G, an instruction is executed to set certain bits in the status register to cause a transition from active mode into a low power mode. So I think the answer to this was false because it's not exactly an instruction. It's an interrupt, which doesn't really count as an instruction. It's an external event that causes it. I think that's how he described it. That's how he would say.
Into a low power mode. You have to.
Oh, wait,
I think this one's true.
An instruction is executed to set certain bits.
Anyone have a?
Oh yeah, no, that is true. That is true. Yeah, sorry. It sets it sends it into low power mode. Yeah, that's
right.
Because
how we've done it in the lab is through an instruction.
Yeah, that's how you. Yeah, I thought it was the other way. I thought it was waking it up, but no, it's turning it off. So that's
when it turns it, or when it turns on, it has to be external because you can't execute an instruction. Yeah, which I think is the next one.
Probably. So yeah. So
could you simplify G? Like simplify it and explain it because I'm not understanding the question for real.
So what'd you say there? It's a little staticky for me.
I was like, could you could you simplify G down a little bit?
So basically, so the simplest way G could be said is basically saying, do you execute an instruction to put your board into low power mode? It's asking you, how do you put a board into low power mode? Or more accurately saying, do you use an instruction to put your board into low power mode? Which if you've used low power mode, like we have in the labs, you know that you write a line of code, aka an instruction, to send it into low power mode. So that's true.
Nice.
Yeah. And then H is the next thing, more low power mode stuff. An instruction is executed to clear certain bits in the status register to cause a transition from a low power mode into an active mode. This is false. So I mixed up this one and the last question with my answer, the last one. An interrupt does not count as an instruction, and an interrupt is traditionally how you wake yourself up. And also, if you're in sleep mode, the CPU isn't executing instructions anyway, so you couldn't even if you wanted to. So you have to use an external interrupt, hardware interrupt, so on and so forth, in order to jostle that thing back to awake to get it into active mode. So he has a note here on this. So he describes why it's false, which is my favorite type of true false problem, the one where it's like pseudo debatable. So he says false. When in a sleep mode, the CPU is not executing instructions. Changing the copy of the status register on the stack to exit a low power mode after an ISR completed does not fit this description. Semantics to a point, but you just have to answer what they're expecting. So you got to say false here. But it also makes sense. If the CPU is asleep, it's not executing instructions. How are you going to use an instruction to wake it up if it can't even execute it, right? You can't. So we got some interrupt questions. You see, there's a lot of true false questions, which bodes well because 50-50 if you have no clue what's going on. But then this one, when a new interrupt request is received, the processor immediately stops processing the current executing instruction before finishing it and starts the exception processing. No, that's stupid. We don't do that. Our hardware does not do that. It does exist in the world.
Oh, I see what it's asking now.
But we do not do that. So if you get an interrupt in the middle of your addition of like two numbers, it will not pause and go handle the interrupt. It waits. In fact, after every single instruction in your code is executed, it checks if there's an interrupt pending.
Well, it would corrupt the code
so
process.
Milankovic did say that hardware like that does exist. There are like architectures built around that idea. No clue why, but it's like some wacky pipelined magic. So it does exist. It's just not, we don't use it. So we don't have to care about that.
Yeah.
So it's not our problem. But as part of instruction execution process in this architecture is the fact that after every single instruction, it goes on to check for pending interrupts. That's how it works. So if this said, when a new interrupt request is received, the processor stops processing or finishes processing the currently executing instruction and starts to accept, then it'd be true. But it's false here since it says it stops it immediately without finishing the instruction. Moving on to B, so that's A is true. Moving on to B, true or false, the retire, return from interrupt instruction.
No, A is false.
Oh yeah, sorry, A is false.
Yeah.
Sorry.
Not
I said it was false, then I went back and boomed it. So the retire, return from interrupt instruction, retrieves both the status register and the program counter from the stack. Yes. Same way the return instruction from just like a standard user-defined function works, it's going to do the same thing. An interrupt service routine is just a spicy version of a function. That's how I've been thinking about it this whole time. And it operates a very similar way in that respect, at least in the exiting. Entering, it's a little, more nuanced, but exiting is very similar. It needs to know where it needs to go back to. So it takes the program counter and it will also return the status register values because you don't want to just leave interrupt flags on for no reason. All right, then C, so that previous one, B, is true. C, if multiple interrupt requests are pending, the processor selects the one that arrived first. No. So let's say, yeah, so let's say there are two interrupts that exist on my machine. One interrupt that when it is received, it will add two numbers or it'll alert me that like it sensed light or something. And then the other interrupt is me pressing the power down button. It will power down. If it sees those two pending, it'll power down. All that illustrates is that there is a hierarchy of interrupts in the interrupt vector table, and it takes the one with the highest priority. We have to assign priority to these things. We can't be checking if light's gone or if we've detected something if we're actually supposed to be turned off. That doesn't make any sense. So we have a precedence thing going on. So this is false. It will take the highest priority one. It will not take the one that arrived first in time. Then there's D, the GIE global interrupt enable bit in the status register can be set inside an interrupt service routine to explicitly by the programmer to enable nesting. Yeah, this is true. You can do that. Mm-hmm. I think I ended up doing that in my final project. It's a real hell of a thing, but you can do it. Don't know if it's a good idea, but that's true.
Going back to number B.
Number B. Let's go.
As a side note, he may ask a question about which gets pushed or popped first. So what happens when you go into a exception handling process, you have to push PC, then the status register.
And you return them in the reversed order.
You return them in the reverse order. And I think that is because you want to have priority of where you're at and then the status register. I don't know why It's that order.
It's
but
probably just how it is, which
PC
means
and
you have
status
to,
register.
so you have to return it in the reverse order. It's just how it is. However it was
Yeah.
sent, it needs to be returned in the reverse order
It
because of how
maybe
the stack works.
maybe because if you like send the next instructions address, okay, so PC, you'll want your current one to finish, and it may update the status register in between that process.
Who
So you may
knows?
want status register absolute last to make sure there's no errors. But
There's probably a good reason for it. Yeah. And then there's E, which is in the case that multiple interrupt request sources share a single entry in the interrupt vector table, programmers need to explicitly clear interrupt flag bits in the corresponding service routine. So this is a multi-source interrupt thing. So you are going to want to clear the corresponding bit in the corresponding service routine. So what this really means is, let's say you have an interrupt that could be activated either from a switch being pressed or pressing Q on your keyboard. And you go in, and what happens is either of those flags could be set. It's just that the hardware sees the interrupt, so it goes into your routine. But within your routine, since it's multi-source, you still have to, within it, figure out where it actually came from to process it properly. And because of that, you also have to reset the corresponding bit to the next nested routine that you make. So you just have to, when you enter an interrupt, it's always a good idea to clear the bit so you
I
don't
think
end
this
up
was
entering over
something
and
we
over
had to
again.
do in one of our labs. I
It
think it's like
was.
port 1, the switches are on the same interrupt. So you have to prioritize which one you want to take first. So if it's like switch 1 versus switch 2.
We've done that. I actually used that in my final project as well. That explicit port 1 interrupt processor where you had to decide which thing to handle, basically, and which bit to clear. But this is true. That's how you handle multi-source interrupts. So that's for E is true. Then we go down here. So it says your task is to design an MSP430 based system that can interface two external devices, each capable of generating an interrupt request. The external devices place a request by setting the request line, which is denoted as a transition from a logic 0 to 1. So it's a rising edge. And then the line is kept active as long as the interrupt request is pending until the request is serviced. Answer the following questions. How would you connect the interrupt service request line, the interrupt request lines coming from the devices to the MSP platform? Well, you would, so you got to remember
a parallel port.
Yeah, a parallel port, and specifically a parallel port that is
Allows interrupts.
Yeah. So you have two options here. So you can use P1 or P2. So I would just co-opt, P1, how we use it for our switches, right? But the thing is, since it is an MSP40, we can't actually just say, oh, we're going to replace the switches. So we just have to pick another, open port on P1. So basically how he responds to this is the exact same kind of way. So the request links the device 1, device 2 needed to connect to any two pins that belong to parallel ports P1 and P2. That includes support for external interrupts, blah, blah, blah. So that's how it is. So you would just say, I'm aware. This question is basically testing if you know which external pins, which parallel port pins are interrupt capable. Because unfortunately, not every pin on the board is interrupt capable. In fact, most of them aren't, which is unfortunate because interrupts are great, but that's how it is. So the answer to this one's rather simple. You just say, I connect it to port 1 or parallel port 1 or parallel port 2 pins because those are the only ones that can process external interrupts, basically how you can get away with answering that. And then G, in a section of the program, you would like to service requests coming from the device ID 1, but not requests coming from the device ID 2. So basically, you would just do an if and then a logic test to sort this out. So these both will set their own flags, right? Like ID flag, ID2, because they're both going to be connected to do different things, right? So you can test. So this is actually, we've done this exact thing. We just mentioned it. Like we explicitly do this ourselves when we're interfacing both switch 1 and switch 2 on port 1, because they're both coming in on the same interrupt area, and we just have to figure out which one to handle. So you can just do a test for the flag of that interrupt. So basically, his whole answer for this is we can reset appropriate bits in the whatever pin interrupt enable register to enable selective masking. So in this area, you could just say, hey, I don't want anything coming from ID 1 in this block. So you can mask the interrupt enable coming from whatever pin you connected ID 2 or ID 1 from, and vice versa. So that's just interrupt enable masking. you could also, well, this one explicitly says that you would like to service requests coming from the other one, but not the other one. No, from one and then not two. So you would mask two and you would allow one. And he answers all of these with just like what amounts to pseudocode / a sentence. You could also like just write the code if you wanted. It's like a couple lines, but I take it most people would prefer to just write the sentence out. But then H is outline the main steps that need to be taken in the main program to initialize the system for accepting interrupts from devices ID1 and ID2. So you pick whatever pins and ports you want to attach ID1 and ID2 to, and then you just configure them. So he chose to go with P2.0 and P2.1 as his connected lines. And obviously we're aware of how to handle this. You would pick your pins, you'd set their direction to input, and then you'd also enable interrupts on the pins. And you'd also enable which change on the pins corresponds to an interrupt, which means you'd have to set it to rising edge, right? And it's 3 steps. You set the pins to input direction, you set the pins to interrupt enable, and you also make sure that the interrupts that they are receiving are based on a rising edge transition.
And then you have to enable global interrupts.
He doesn't say this one because he said
Oh,
he doesn't add that one. I think that's kind of just assumed. Because the question is what? Outline the main steps that need to be taken in the main program to initialize the system for accepting the interrupts from. I guess you could add it, wouldn't hurt.
I do to be safe.
Yeah, it wouldn't hurt. Yeah, there's that. And then I is a 4.1, outline the main steps that need to be taken inside the ISR. So this is where you do like the if branching that we're familiar with. Yeah, see, so his move for this one is he just calls it P2 ISR, right? Like how we'd call it in our thing is like, I mean, we name them, but obviously the pragma vector name for this is like port 1 vector or something. I believe it is port 1 vector. And then you just have go into your interrupt, and then you have 2 ifs. So then it says, yeah, okay. So you test for both of them pending. So you could pick 1 or 2 to check first. We'll just do it sequentially. So you say if ID1 interrupt is pending, then you move into that branch, you clear its bit, it's an interrupt service bit, you process it, whatever that is, and hit the red tie. And then you hit it with an else if that didn't occur, checks is ID2 pending instead, clear its IFG bit, process the interrupt, so on and so forth. So basically you handle everything there because if both requests are pending concurrently, since it hits the ID1 logic first, it'll move into that one and you'll be good. And since it says only one request can be processed at a time, it'll handle ID1, leave the interrupt, note that the interrupt is still enabled for the port, but not for ID1. Now it's ID2 since they're concurrent. They'll go back in. ID1 is now still disabled. It'll skip that branch this time and then handle ID2. So you only need basically 4 lines here. 6 lines if you count the red tie, but make sure you include red tie because otherwise you're not leaving. But otherwise,
well, if it's C, you don't include red tie.
I know, but he did for some reason.
Okay.
Good enough for me. Yeah.
Hey, Ethan.
Yeah, what's up?
But before you start on part 3, could you one more time summarize interrupt nesting?
Well, so let's take for example. Here,
It was a little bit up earlier in the.
No, I got you, Joe. Watch. Actually, I know what to do. I will pull up my my code for my final exam. I have a nested interrupt routine in that. My final project. I have a nested interrupt routine in there for port 1. I'm sure everyone's done this one, but it's, I guess, good to understand it, particularly in C, since he says we'll be heavy focused on C during this anyways. So let me move into this. Bonk. All right. So let me just go like down to the bottom.
Nice flow chart.
Oh, it's a good dude. Look at the servo arm. It's hot. All right. It's all the way at the bottom. Nope, it's farther. Right here. This is where it is. Yeah. Look at this top tier programming. All right, this is the port 1 vector right here. All right, fun. Everyone's favorite vector for handling switch 1 and switch 2. Now you see, you see mine looks weird. I just say if switch 1, switch 2, right? So in reality, you want some type of Boolean test here, but I did some, math magic all the way at the top. Wait, no, all the way at the top of the code, sorry, where I defined these as Boolean tests beforehand. So I don't need to shove it in later. This is actually like best practice for interfacing switches, in my opinion. This handles all of it for you, but we'll just go back down. So this is basically treat those switch 1 and switch 2 calls as testing if the flag is pending, basically. So you go in, you test if switch 1, move in here, do your thing, hit a reti, basically. This is C, so it's a little fuckier, but what essentially happens is I could press switch 1 and switch 2 at the same time, and it would enter either way. Regardless of the order I press, switch 1 or switch 2, it goes into this port 1 vector. So if it's a multiple source interrupt, every single possible source that can enter it within the service routine itself, they're all going to port 1 vector. The vector, it's blind. It doesn't know what brought it in. Something just got in. It just doesn't know what it is yet. So you got to go through and you got to interrogate it and say, hey, are you switch 1? And it'll say, nah. If you say, oh, are you switch 2? It'll say, nah. It'll be like, oh, are you switch 3? Blah, blah, blah. And then it'll say, finally, yeah, I'm switch 3. And then you can handle it, leave, right? So that's all it is, really. You just you interrogate the source. You got to find out where's this information coming from, right? You got to hit it in the knees with the baseball bat sometimes. You know, that's how it is. What's in the box, right?
Okay, makes sense.
Yeah. Bonk. Yeah, that's that. All right. Fun. Look at this. Yeah, let's go. All right,
Yeah, buddy.
Let's go. This stuff's fun. This is definitely gonna, lay some people out on their asses, unfortunately. But it really is just, funny math. So basically, it wants you to drive a sensor. It'll want you to drive a sensor to provide the following signal, which is y is equal to 1.5 times sine squared of x. As shown below, it defines you some values, right? To accomplish this task, we'll use the digital analog converter peripheral and a lookup table prepared in memory, similar to our exercises. So we all did this. So it says, what's the maximum minimum output voltage of the input? Now, he mentioned that, you'll be given these figures most of the time, but they're not inherently helpful, right? So they might be like, if you're focused on this might be wrong or something like that. So he said, it's good to do the math out yourself, but even so, what's the maximum and minimum output voltage of the analog output, right? So thinking about it, sine squared is just, squaring of the sine function, nothing too special there. So think about the range of inputs that are possible. It defines x for you as 2 pi f times t, and f is defined as a constant. Now, if you know the properties of sine, you can disregard the f as a scalar and just remember that it's 2 pi. So basically, anytime that 2 pi is left over, integer multiplications of 2 pi, every time t is equal to 1, 2, 3, that kind of stuff. Wait, no, is it 2 pi or pi? Every time it's equal to a half, I believe it's at its maximum value. And every time, actually, no, it's because of the 2. He squares it. He squares and he changes it here.
Yeah, it'd be pi over 2. It'd be at its max and min.
Yeah. So pi over 2, which means, oh, yeah. So that's every time x is equal, or every time x is equal to 0.25.
All you really need to know is what values does the sign put out as a max and min?
Well, it's going to be
and
1
then what are
0.
those values times 1.5?
Yeah,
so 0, 1, 0 times 1.5, 0.
Sine squared will still yield you maximum of 1 and 0 and minimum of 0. Now, in his thing, the thing is he wants you to find the values. He doesn't say it explicitly, but he answers it at least. So he writes out the max to be 1.5 volts, as we know, because sine squared can still only output 1 at peak. So multiply 1 times 1.5, you're going to have 1.5. And that's found at x is equal to pi over 2, and sine of x is equal to 1. So when x is at pi over 2, sine of x is equal to 1, square sine of x, still 1, and now you're 1.5. And you can see that on the figure because 0.25 is its peak value. So in this case, it's helpful. And then he wrote max twice when he meant to write minimum, and his minimum is 0 volts because, whenever sine hits 0, the whole thing's going to be 0. And sine should hit 0 every time x is equal to 0. or every time x is equal to a half to yield sine equal to 0 because it'll be pi. And it doesn't like that.
Yeah.
So then you have to, then it says, you know, what reference voltage do you want to generate the signal? 1.5 volts is fine. That's easy peasy.
And then R or VR minus is 0. So
Yeah, but in this case,
simplifies the equation.
he only wrote VRF for some reason. He only wrote 1.5 because I guess you just
the other
assume
one
0.
you just ignore. Yeah.
And then it says, what is the duration of one period of the wave signal y in milliseconds? Okay, let's think about this. One period, right? And it's in milliseconds too, so keep that in mind. Oh, well, we have its frequency, which is a lie, isn't it?
Is it just 0.5 seconds?
Yeah, I think the frequency here, if you were to work off the
Looking at
frequency,
graph.
yeah, you got to look off the graph, because if you work off the given frequency, it'll be wrong. Because the frequency is scaled within the sine squared, so it's going to be different. So otherwise, you can look at this, set this thing, looking at a sine function. It is 0.5 seconds.
Yep.
Oh, the scale is in milliseconds, so it's actually 0.5 milliseconds. So you just write 0.5 milliseconds. And that is the right answer.
That's important to pay
There's
attention
the scale.
to, is the stinking units. Oh my god.
The scale's hidden over here in the corner. So be careful about that. All right. Answer that. Let us assume we work with the table. Yay.
I always struggle with the lookup table.
Yeah, so
No.
let's get it. Gamer time.
So you take samples. What did it say the sampling frequency was? 10 samples for a single period.
Yeah, but it says 10 samples for a single period, but the thing is it's symmetric. So he gets away with 5, because then you would just revert this and go backwards in the same direction at the same rate. So you can, so that's why he only gives us 5 slots. So
well, you could draw it on the plot. Actually, no, you can't, because this is not a paper exam.
yeah, exactly. You can. Well, I recommend bringing paper and drawing this out. It'll definitely help. But it wants you, and it even says sketch the output signal. That's not going to happen. That question won't show up in the form of actually
technically the sampling
sketching it.
frequency is 10 over 0.5 milliseconds,
Yeah,
which is 20 kilohertz.
But even so, we don't need to mind the sampling here, or frequency here. We can just know that if it wants 10 samples in a thing, right, and it's 0.5 milliseconds, then it's just going to be, you know, what is it? Divide that by 10, and then it'll give you your time shift, your time increment each time.
It's like 0.05 milliseconds is the time
it's one
moving.
down. So you do this 3-4 times here, since it's symmetric. You only need to go up to 5, and he only gives you 5 slots. So
could you write it?
do.
Are you able to like annotate it?
Yeah, here, let's see. So
if you have a graphing calculator, this helps too,
let me,
because then you can just
we'll
move
just move
your
it up this way.
trace to wherever that t value is.
Yeah. So one period is designated as this whole first start, right? But then you've observed this sign and you realize, well, this thing's symmetrical. So you can cut it down this way too. So this goes to 0.25 milliseconds, right? To the middle point. And the whole period, as mentioned over here, is 0.5 milliseconds total, right? And this says lookup table with 10 samples for a single period, and it says first 5 samples, right? And it gives you the first sample. Thanks a lot for the 0, real helpful. All right, so so you think about this, you say, all right, 10 samples in one period. Well, what does that mean? One period, 0.5 milliseconds. Divide that by 10 in your mind, and just shift it over 1 decimal place. Not too bad. And now you have this. This is your time increment change, right? So this means every next sample of time, the time in seconds is just going to be 0.05 milliseconds, add 0.05 again. Now you're at 0.1 milliseconds, 0.15, 0.2. That's it for this. So that's how you get your time. And then guess what that means you can do? Just plug t, which is the only thing that changes, right? Of the sine squared, remember, right here it says sine, right? But it doesn't, I mean, if it only actually, does it actually only want us to put out the sine value there? Because otherwise I would swear.
Because he did that in the homework for some reason.
Yeah, okay, sure. You'd fill this with sine, which I guess it's an intermediary step, but this in itself is not valuable because you don't use this value to convert to volts. You have to square this and then convert it to volts because we're operating with a sine squared, as we mentioned. So this is plug and chug. Once you find your time range, you populate it down this. That's easy enough. So I'll do the first and the last one. 0.05, right? And then down here would be 0.2. And then plugging in this to sine is just an, calculator magic, but he did it for me. So I can just go over here and just say 0.309. Right. And then down here is yet again, you just plug this into this function and it'll spit out 0.951. Nothing too magical there. Just plug and chug. Now for your volts, right? Well, now you got to take these numbers and square them first to actually produce Y, right?
And then we'll square, then multiply by 1.5.
Yeah, square this and then multiply it by 1.5. So you square this value that we got from this column. Really, this isn't even like a rule. You just have to follow, like, keep this function in your mind. Whatever the Y was given as, you just like, when Y is given equal, you just plug in the data, The only thing that varies is T, right? So you just plug in the T you calculate everything else, including your Y, and then you have to, convert it. Which the math for converting this is 4095 times your Y divided by your VREF, right? To produce your lookup table value.
The
So
whole
that's-
equation might be useful to write out. Do you
Yeah.
know it off the top of your head?
Yeah, I just said it.
No, I mean like the whole ADC equation.
That's stinky. It's never useful.
I'm quite sure he'll probably change VREF to like 0 or something stupid.
That wouldn't make any sense. They do that, and then, but no, I don't have it off the top of my head.
I can list it off to you if you want.
Yeah, so this is the one he uses for this, but sure, what's the full
The
full
full
equation?
one is nearest integer of, so you take the nearest integer of the value. In parentheses 2n minus 1, which is where you get the 4095 because it's 2 to the 12 minus 1. And then that times the fraction on top being your ADCN minus your VR minus. Yeah, VR minus. And then over VR plus minus VR minus. So since VR minus in this case is 0, it's ignored. But for what it's worth, that is the entire equation.
I've never used it like that. I always reduce it. That's stinky. I don't like it. But no, he's almost always given us, and particularly here, like in all the instances, because it's a DAC 12, it's a 12-bit DAC. But 4095 is the standard number. I don't think we've seen another one, maybe in a homework, but even then I think it was always 4095.
Oh yeah, the ADC 12 is always 4095.
Well, this is a DAC 12.
But he could say like DAC 8 or something stupid,
I mean, in that case, just know that where the 4095 number comes from, it's just 2n minus 1 to the n minus 1. But yeah, so
Right. So the formula you have right here to the right, that's going to help us with.
This is this questions. This is this questions. This is like once you've calculated your Y, you multiply 4095 divided by the VREF
times Y.
Yeah, that's the whole thing, and that's gonna equal your number.
But that's gonna go under the.
That produces all your lookup table values. These will all be in decimal, and then over here it just wants you to convert them to hex for the hell of it. That's easy. We don't need to look at that. That literally is just taking decimal and turning into hex.
The calculator comes in handy.
Yeah.
I got a different number. I got a different number for sample 4 than he did on his solutions.
Sample 4 for which column? Where did it
so
start
I got the
to
same
differ?
for in Y.
Yeah. So what'd you do? Did you get the same sign value as him?
I think so. Let's see. Yeah, I did. Yeah, because I got 0.809.
Did you square the sign value?
So let's see. I'm gonna do it right now. So 0.809, and then you square it. That gives you
Yeah.
0.654, and then you multiply it by 1.5,
Yeah,
and that gives me 0.98.
Hey, that's what I got.
0.982.
yeah, it
That's
looks like,
exactly what
looks
I
like
got.
he did not multiply by 1.5 for some reason.
There you
Okay,
go. He
Just making
just-
sure I'm not missing something.
Yeah, that's an error on his part then.
Yeah, you want to make sure, that's why I said, like, make sure you're focusing, like you're paying attention to this formula, whatever they're giving you. Make sure you just like mindlessly plug and chug. That's how you solve this table part. Lookup table is you just, take however many
Mhm.
bits, divide by your vref minus your, whatever your lower vref plus, vref minus. Because
Mhm.
of the hardware we're using, it's almost always vref lower is gonna be 0 volts.
Mhm.
Because we.
I mean, the
can't-
in the homework it wasn't. So
Yeah,
that
we
tripped
can't
a lot
get
of
a,
people out.
yeah, we can't really get away with negative reference voltages on this since we can
Yeah,
only
so
really
what's reveal?
positive.
What's be real for this case?
1.5 volts.
1.5.
We
yeah.
decided that over here. You're the one, it says, it asks you, what is the reference voltage used to generate the required signal? So the lower reference voltage is 0. Because what's the voltage range here? We have a 0 volt minimum and then a 1.5 volt maximum. So 0 volts would technically be your lower range reference, but that's implicit. And then your higher range is just 1.5. Right. Because that's the peak. We don't need any more voltage reference to generate 1.5 because we're not going any higher than it. So we need the minimum and the peak, but the minimum is implicit at 0. That's just how it is. So in
Cool.
reality, this formula looks a little more different, where it'd actually be vref minus vref plus, which is 1.5, minus vref minus, but it's 0, so who cares? And then just say vref instead. And 4095 is the 2n minus 1 quantity from however many bits, in this case 12 bits, you have in your DAC or ADC. And then y is just, the production of the function. And then that's how you generate these lookup table values. So he calculated this y wrong, it seems, on his solution because he didn't multiply by 1.5 after squaring his sign. So his numbers are off.
Lovely.
Get played, stinky.
Probably changed the equation. Forgot about that part.
Yeah, maybe. Even so, lookup table hex, all the fun. This stuff, like y is how you produce. Once you've found all your y's, which is, the
Mhm.
result of this equation, you just shove the y into this formula that you generate this formula on the fly based off this information. But it's going to look very similar to this. Populate your lookup table values in decimal, convert them to hex. If he even asks that, I don't know if the hex will stick around. But if he does ask for the hex value, really not that tricky. So that's not the hard part here. So then that's that. So I'm going to do that. I said do that. And then that, so I can scroll. Yeah, and then it says sketch the output analog signal for the first whatever, right? So this is the drawing of the
Half a
ugly ass.
millisecond.
This is the drawing of the ugly ass square. So now I don't know
The ugly ass
because
sine wave.
yeah, I don't know if doing this digitally, if he's gonna have like multiple choice with a couple pictures of it or something. If that shows up, that's how the only way I can think of it. So
Yeah.
let's think, right? So you would populate this table, and really all this is you just, do the thing. So 0, you get your first point, 0, yippee-ki-yay. And then what's the next one? It was like 0.05, right? So 0.05 is gonna
halfway
be
in between.
over here, right? And then it
Yeah.
just looks like this, like, oh, and then you go, oh, you go, oh, whatever, wherever
You
this.
skipped too far. You skipped too
But
far. Too far.
but we
I
get
was-
it. Like
think-
every
I think I'm
period, every
actually-
little sample.
Yeah, I did skip too far here, but yeah, so it's like that. So let me erase this and fix it. So it
And
should,
the like approximation to that wave always trails roughly behind
something like this.
time wise.
Oh yeah, but then it gets even
accuracy level.
funnier though, because let's say we go boop boop, and then what happens?
It overshoots. So your average value is a little bit past that.
Yeah, I overshot it there, but yeah. So this is what it'll look like. It'll look like this, right? If your sine waves are looking like this, call me. All right. So that's all I got.
Need that RC filter in there.
Woo! Let's go. All right, timers, let's go. All right, fun fact. I sat for 3 hours at a computer figuring out how to use a timer to control servo motors. Not fun. I killed 2 servos. All right, if we use a timer A ISR to control sending the next value to our DAC, how many interrupts per second should timer A generate? Well, we need to know the frequency of how often to populate this. Well, we know that's 0.05 milliseconds, so calculate frequency there. I think you said it was 20 kilohertz or 20.
Yeah.
Yeah, 20 kilohertz for Sydney. We can do the math. So 0 Okay, it's actually gonna be like. Anyone have a calculator in their hands? Mine's like 5
Me.
inches away. It's a little far from me.
I have it.
Yeah, so if you do 1 divided by 0.05 milliseconds, that should yield the frequency of 20,000.
20,000.
Yeah, perfect. That's how you calculate that. Because guess what? I deleted the doodle. Well, our funny little doodle had a straight line, then a jump, straight line, then a jump. What does that jump signify? It signifies that a new value has been made available on the DAC register. Who put it there? The timer. So you just gotta, if you're using the timer to control that, every time you need a new value to be there, the timer better generate an interrupt to do that. Like you better generate an interrupt to do that, right?
Mhm.
But you can overshoot it too if you want. But let's see what he says. Yeah, 20,000 a second, easy peasy. That's what he says. No problems there. And he says if frequency MCLK is equal to frequency SMLK is equal to 1 megahertz, how would you configure timer A? Well,
Oh no.
when I use timers, I always use submain clock as my source. So you can select SML clock as source for your timer, right? Then you pick your timer mode. I exclusively use up mode, and he also agrees with that. And then you set your TACCR0, your peak, right? So what does that mean you have to do? Well, you have a frequency, your source frequency is 1 megahertz, right? And then you have a required frequency of generation, a frequency of interrupts at 20,000. So what do you do?
Wait. So the answer to E is 20,000?
Yep.
Yeah.
Okay.
Easy peasy.
Yep.
So, in fact, if you answer E wrong, you're going to get F wrong because it's integral. So if you need, by now I have a disgusting amount of experience with timers because I'm a sad little boy, right? So all you do here to get your R0 value, that is your peak count, which also counts as, if you have nothing else and just that value, that every time it reaches that count, it'll spit out an interrupt, right? So you need the decimal number to put into the register with your source clock, so you actually can count, to your 20,000 a second, right? To your 20,000 hertz. So to produce that, you do 1 megahertz divided by 20,000 hertz, and that will spit out a decimal number for you.
That will, I mean, if you ever get confused about that, just check units because you
Yeah.
want it to be in
nothing,
a number.
in
And
unsigned,
no like
in
seconds
yeah,
involved. So by
nothing.
dividing
Hertz over hertz
will
is
be
going to
done.
be nothing on non-unit. So when you do this, he does 1 megahertz divided by 20,000 minus 1. Now I don't use the minus 1 thing because it's not really necessary, but I think the difference here, I mean, he just does it that way. Is there a reason for that? Because I don't do that. Mine's work fine.
Because you start counting at 0.
Yeah, there it is. Yeah. So doing that yields 49.
I've never done that though.
I don't do it. I mean, for me, I don't do it because it's not necessary.
It
You'll be
won't
off.
make enough of a
Yeah,
difference.
you'll be off by like 0.001 hertz, and it really doesn't matter. Like my frequency was 49.99 hertz. Right, I had no necessity there. All right, but that's all it is. And the value here, 1 megahertz divided by 20,000, and then subtract 1 from that quantity is 49. So that's just the number you shove into the timer TACCR0 register for timer A. Make sure you know it's CCR0. If you don't have a CCR0 value, nothing's happening with your timer.
Wait, so for part L, I had did 1 divided by, I did
1
divided by
megahertz.
20,000. Oh, okay. That's
Never
one.
mind. So it's 1,000 hertz divided by 20,000 hertz minus 1. So you do the whole thing, then subtract 1. It should be equal to 49. And you subtract 1 because it starts counting from 0. Right, yeah. And then there's G. You wrote the timer A ISR that reads an entry in the lookup table, increments the table pointer, checks its range, and sends the value to the DAC12. By profiling, you determine that the ISR requires 20 processor clock cycles. Is it possible to implement the sine wave signal generator? Yeah. Is it possible to implement the sine wave signal generator under these conditions? Elaborate your answer. All right. I love how like scam email-y that phrase sounded, but let's hit it. So 20 processor clock cycles. We've been told that our processor clock is 1 megahertz. So we need to generate. So basically it's asking us, can we make this faster? Yes, because 20 clock cycles. So all you do here is you just find out, how many seconds 1 megahertz yields, right? Multiply that by 20, and that'll show you how long it takes for this whole ISR to execute. So what is that going to produce?
You
What are they,
basically
6?
don't
Could
want to
be
be
1
reading in
microsecond.
values
It'd be 20 microseconds.
while you're calculating. the whole
So
point.
in this case, all you have to do.
I believe
So-
it's 50 clock cycles.
So yeah, he says his
per-
answer is he says timer A generates an interrupt every 50 CPU clock cycles. The time required for the ISR is only 20, so yeah, you can speed it up, and that's true. The math here is relatively simple. So go back to all that timer information. Where did we fundamentally get that? Well, actually, no, we know. I mean, previously we just did the calculations. 1 megahertz divided by 20,000 minus 1 equals 49. But if we're just talking about absolute speed here, it's actually 50 instead of 49. So that's 50 clock cycles. And we've been told the ISR can operate in 20 cycles. So really, yeah, we can speed it up a heck of a whole lot. We could double the samples and there still wouldn't be a problem. So yeah, you can just say, you basically just have to say, compare the clock cycles with that answer and then just say, yeah, you can go faster. Then that'll get you credit. And 4 is how would you improve this design? Funny. So he's got a couple improvements here. So one I mentioned at the beginning, which is something you should always be looking for, which is signal symmetry to simplify your table. I don't want to have any more values in my flash memory than absolutely necessary. So you can reduce the size of the lookup table and exploit symmetry, which is, good move. It says you can consider fine resolution because we can speed this thing up. So as mentioned, I joked earlier that the sine wave looked like trash, and it did. If your sine wave looks like that, don't actually call me. So basically, we can speed it up. That's another improvement. We can speed it up a lot, double its speed entirely. It still work perfectly fine.
You could also implement Nyquist's theorem
Silence.
by just literally
I don't want to hear
only
it.
taking 2 samples per period.
I don't want to hear it. And then you can say, use DMA to transfer samples from the memory to the DAC12. So that just speeds things up even more. Why use an ISR? Well, you can just use hardware that exists solely to make shit faster when it comes from pulling stuff from memory and shoving it somewhere else. Memory manipulation is the DMA's, bread and butter, and it's very, very, very fast at it. Much faster than an ISR could be. So you could make this even more ridiculous by using the DMA. You could probably triple, quintuple, pentuple the speed and resolution of the signal. Fun, fun, fun. More timers. Let's go. All right. The MSP 430's clock module can internally generate clocks used by the processor and peripherals or use external crystal oscillators. I believe this is a fat true. We literally have external crystal oscillators on the MSP board. If you've never taken a real good look at the blackboard, for example, schematic, you can actually look at the schematic, find what pins the stuff's attached to, then look at the board and straight up find the physical crystal sitting on the board. That's an external crystal oscillator. And then it also has the internal peripheral to do that as well, which is its clock module. So this is a true. Then there's B, which is asking about these little clocks. So main clock, sub-main clock, and auxiliary clock are fixed and cannot be changed. That's a false.
Baloney.
That's big baloney. The whole purpose of
can-
the clock module is that you can.
Yeah.
If
You
it
can
only-
divide them by like
Yeah. If it only had the external oscillators, then there'd be a little bit of a problem there. But it doesn't. It's got the module. All right, and then there's C. To prevent a controlled reset of the system, the watchdog timer in watchdog mode requires a hardware signal to clear its control bit before the time period expires. I think that's false.
Yeah, it's software.
Yeah, it's not a hardware thing.
Literally the only reason the watchdog timer exists is to generate some signals. And if you're using it as like a controlled reset thing, it exists in case your code freezes and it's not pet within a certain amount of time.
Yeah, it'll just say
Um,
reset.
Yeah.
That's why if you don't turn the watchdog timer off in our early programs, it would just run over and over and over again, since you had like
Mhm.
5 lines of code that would run immediately on execution. So the watchdog would just spam this with output. So that's false though. It's software, not hardware controlled. And then D, and you know that because we've literally been doing that this entire semester. Everyone, never forget to turn off your watchdog timer. Then there's D. Timer A can be configured to generate a pulse width modulated signal without intervention from software.
True.
Yeah.
I did that for my final project.
Yeah, I think I did as well. These
because
timer
it
beat up.
utilizes hardware side capture and control systems
Yeah.
to do that.
Yeah. You can-
Could you explain D a little bit more? Okay, so I'm not understanding why D is true.
All right, so D is saying timer A can be configured to generate pulse width modulated signals without intervention from software. So we're all aware that we
Excluding
can,
initialization.
yeah, so
That's important.
we all know that we can generate PWM directly in software with the timers by, manually updating the timer registers, the compare registers, and changing the duty cycle of the signal, right? You set your total length of your signal with your CCR0 register, and then you can pick any number of like the R1 through however many there are, R6, who knows, right? Registers, and those values will all independently generate their own PWM signal, right? When it approaches and generates an interrupt. But the thing is, you can also do it in hardware. Wait. Yeah, you can also do it in hardware. It's saying without, it's asking basically, can you use hardware as well to achieve this? We know we can do software, but you can use hardware as well, as Sydney said, with external capture and control stuff, hardware blocks, where you can give it a reference or information on some
I
pin.
think we did that in the lab with the buzzer because we had the buzzer directly driven by
Yeah,
the
but there's
timer
also,
pin.
I think there's also the fact that you can set like the multiplexed register pin, like the register pins or whatever with
Yeah.
as like output or input, right?
I
And
do not remember how to
I
do that.
used mine as output, but you can set that to input, and that means anything that goes onto that pin is being used as capture and control, which will thereby control the value of the register, I believe.
Yep.
So yeah, that's a fat true, and the answer key says true as well. So basically, you just need to know that there's a special set of circumstance where you can use it hardware exclusively to control the timer A's PWM.
Okay.
Yeah, and then also just the sheer fact that it uses interrupts
Yeah.
to actually time when we are doing everything by software. The interrupts are hardware based, so in every sense, it is true, pretty much.
Yeah, and then the next question is literally confirming that it's the truth, because it says, what does it involve? What does it involve capturing an external event in timer A? External event is not software. We know that. So that means you can control timer A, you can capture it, and then use that to, make some stuff happen. So it's saying what happens inside the timer. Well, when the external, here's his answer verbatim. When an external signal changes, the current content of timer A counter tar is latched into one of the capture and control registers, CCRX, which later can be read from software. What does that mean? In short, I attached an accelerometer to pin 3.4, which I happen to know is timer B's CCR3 multiplexed pin on input mode, and I sent something in, which is then read and captured and held. It's just shoved, like you just shove something on the pin. That's your external. The external signal changes, current content of the timer is latched, and it's sent to a capture and control. You're done. Easy peasy. You basically just send a signal onto the pin, right? But that's all he says for it. So then he's got this big old brick of a question that's only worth 3 points. So it says, let us consider a program that displays time on the LCD, our favorite peripheral we never used, of the TI's experimental platform. The time is displayed with resolution of 1/10 of a second in deciseconds. What the processor wakes up periodically, updates local time variables, performs necessary format conversions, and displays the time on an LCD in the following format: hours, minutes, seconds, days. Or date. Is that date or date? I don't care. These steps,
It's like decimal of it's a fraction of a second.
stinky. These
Which
steps
is
take
worse.
n equals 2000 processor clock cycles, during which the processor is in active mode. After that, the processor goes back into low power mode. The MCLK in the active mode is 1 megahertz. The platform draws 1 milliamp when the MSP430 is in active mode, and 0.1 milliamps when in low power mode. What is the total active and sleep time during one application cycle? Calculate the average current. Yay!
Well, it's going to be in between
Let's
what?
go! Let's go!
0.1 and 1 milliamp.
You know
You
that
get
at
it
least.
outside is wrong.
You know that at least. All right, so let's take some information. All right. First piece of information is the fact that changes occur every 1/10 of a second. It wakes up every 1/10 of a second, does all the updates, calculations, display, and then goes to bed. And it says these steps take 2000 processor clock cycles during which the processor is in active mode. So we can assume, and then it says after that. So every 10 seconds, 2000 clock cycles occur during active mode. So it's consuming its 1 milliamp during that period of time. And then it drops back down to 0.1 milliamps when in low power mode. So first we need the total active and sleep time during one application cycle. So what it means by application cycle is how often does updates occur? And we know that it's 100 milliseconds. So you can say that to start. And now you got to calculate the active. So we know that 2000 clock cycles are important here, right? 2000 times the main clock frequency is going to give us how long it's active. So 1 divided by 1 million, or 1 times 10 to the 6th power, times 2000 spits out, let's just move the zeros down. That's 2 milliseconds. Move the zero 6 places over, and that's 2 milliseconds.
Yeah, 2 milliseconds.
All right. So what does that mean for us? Well, we have two pieces of information. This bitch is only active for 2 milliseconds out of its application cycle of 100 milliseconds. So therefore the time high power is 2 milliseconds and the time low power is 98 milliseconds. Well, quick maths time. How do you calculate a weighted average?
Well, it's
yeah,
so something over the total. In this case, time.
So the weighted average, we have 2 milliseconds, we have 98 milliseconds. So you do 2 milliseconds divided by the total, 100 milliseconds, times 1 milliamp, plus 98 divided by the total, 100, times 0.1 milliamps. That'll equal 0.02 milliamps plus 0.098 milliamps. You fucked that up. I think you fucked it up.
I
It's
get
quick.
0.118 milliamps.
Oh yeah, no, that's good then. There you go.
Is that right?
Yeah, it's that. Then his
Oh,
is right.
rad.
He just wrote something big wrong. But yeah, that's how it is.
So it is in between the two.
Well, of course it's gonna be in between.
Sanity checking, Ethan. We have to be able
Okay,
to
fine.
check.
But yeah, so it's just this is a weighted average. So it's not actually that hard of a problem. It's just weird because we've basically never done that type of problem. I don't even remember if it was on a homework. Maybe not.
It should be on the exam. I would hope not.
Well, if it is on the exam, it's actually not that tricky because you only need a couple of pieces of information. You need the source clock, which we know 1 megahertz. You need the application cycle, which was given at 100 milliseconds. We need to know how long it's in either cycle because we don't need the length of time explicitly given for both cycles. Since we're given the application cycle, we only need the time for one other cycle. It was given to us in a roundabout manner by telling us, hey, it's 2000 clock cycles active. Well, you can just convert that to time via the main clock, which was given to us. And then you just need to know how much current it consumes during either period. And then you need to know how to calculate a weighted average, which, might be a big ask because no one does that manually. But, it'd be like that. So then in G, it says calculate the total power in milliwatts. If we power the platform by 2 AA batteries, thank God he told us it's 3 volts. Determine the system operating time in days. If we know the battery capacity is 2500 milliamp hours, this isn't going to show up on the exam.
Yeah, this one's the one that's
I
not
know
going to show up.
I know
but
it's
we're
not
electrical
gonna show
engineers. We
up.
can do this.
I know it's not going to show up, but oh well.
If it shows up, we all can just turn our tests in.
Yeah, so we know this. So what's everyone's favorite equation for calculating power? It's P is equal to IV, VI, however you'd like to have it. So we have the average power consumption already. And it just gave us that it's powered off 3 volts. So you do 0.118 milliamps times 3 volts. That gives you 0.354 milliwatts, right?
Mm-hmm.
Now you got to calculate the time
How
right?
many days?
Yeah.
So the easiest way to do this is probably to convert milliamp hours to milliamp days. Would that be dividing
Nah, you don't
by
even need to do it. All you can just take
24?
milliamp hours and divide it by the average current consumption, and it'll spit out hours. Just think of the
Oh, and
units.
it just works.
Yeah, milliamp
Oh,
hours
lovely.
and milliamps divide by milliamps, you're left with hours. You know, everyone loves units. So if you do 2,500 divided by 0.1, 0.118, because they're both in milliamps, don't need to do any magic conversions there. You will get approximately 21,186 hours, which is
Divided by
882 days.
24. Yeah, there you go.
That's
Is that
Pog.
correct?
Yeah,
Lovely.
yeah.
How many days you got?
882. It's like 2.5-ish years.
So this is what they put in those air tags. Except there's no LCD. I didn't think about that one.
There's no way in hell this thing would operate for that long.
There is no.
If there's an
way.
LCD, I don't want to
no,
hear
a watch
it.
battery. A watch
They're
battery
scamming,
might.
bro. They're scamming.
I mean, how long does your like Walmart watch last? 2 years, roughly.
I don't know. This is a scam, bro. I don't want to hear it. It's a scam. All right. They're pulling free energy out of the wall. All right. Outline briefly organization of the program that displays time. List peripherals, needed initialization. All right. All right. So the reason why this is a big oof is we were never explicitly told to use the LCD, so almost nobody knows that the LCD controller is a thing.
Yeah.
But you're going to need that if you're going to use the LCD as it requests. We have no choice. So you're going to need two things peripheral wise: timer A and the LCD controller, right? So as mentioned, you set timer A to generate an interrupt every 100 milliseconds. So figure out the numbers you want for that. So he explicitly says he uses up mode with MCLK divided by 8 clock as the source clock. And then he divides the math and he just ends up putting the value 12,499 in CCRO, right? And then you got to go the LCDA and do the MUX thing. But as mentioned, since we don't know about LCDA, because we never use the LCD controller, we would get smashed on that, which is why this question explicitly probably won't show up. And then you are going to need to make the timer A ISR since you're updating the values on the LCD, right? And you're going to need local variables as well to hold those values that you're shoving. And then just do a main loop where you enter low power and then an interrupt occurs off the timer, wakes you up, update values, go back to sleep, and do that forever until your
And it's
batteries
just
run
a
out.
bunch of nested if statements for the ISR.
But the thing, I mean, it is, but you know, in this question, it's strictly like pseudo code. I don't see a single line of code written.
Yeah, basically you have to know that you do like somehow you send the message. He could ask this without us knowing those.
Well, he'd ask it
things
about
and just,
something
like,
else.
ask pseudocode.
He'd maybe have it like send it to UART or something.
Yeah.
Yeah, but even so, you just gotta really the real difficulty here that you'd have to like is setting your timer CCRO 0 value because he decided
from 0 to 10. What's the likelihood of this question ending up on the final?
this exact type of question, like a solid 1.
Yeah, 8. Okay, cool.
Like this thing because it's solely because it uses the LCD. Now I could see, as mentioned, him deciding on something different, like
Yeah,
oh,
say
we'll
like
send
an
it to
LED
UART.
I
But
just know
really,
that LCD was optional for the final project, but
well,
nobody
yeah,
used it.
like that's the thing. I think maybe 1 or 2 people used it from my recollection, which is why it's very unlikely it shows up because it's also peripheral. We really just skipped. We did not discuss that thing. All right, even so, moving on to more of these funny monkey communication problems. Oh boy, 2 devices A and B are communicating using a bidirectional asynchronous serial link. How many signals need to be routed between the devices, excluding the common ground? Well, let's think about
it's
this.
bidirectional asynchronous.
So you gotta have
be
a way
UART, something like UART.
to transmit and receive, and that is it. So a TX and an RX lines, it excludes the ground, so we don't care. That's it.
And there's no shared clock, right?
Yeah, it's async. Just
So
TX
it's
RX.
literally 2 lines.
It's UART pogloot.
There you go.
Poggers. All right, that's it. So that's all you literally just write 2. You don't even need to specify it as transmit and receive line, but you could. Good practice.
Two's the answer.
Yep,
Yep.
but 2 is the answer. So what is the total number of bits transferred when a single character is sent from device A to device B using an asynchronous serial link? Assume the following: 8-bit character parity is on 2 stop
Two
bits.
stop bits.
That means parity is gonna slap an extra bit on that, John.
Mhm.
Because you need to no, it doesn't matter if it's even or odd parity. Either one will shove an extra bit on to make sure it's things working. So that means we have 11 bits total. Is that it? No, it's a lie. It's a scam.
12.
It's a scam.
12.
The start bit.
The start bit. Never forget the start bit.
I've been scammed.
It will never be specified, and it
I
will
will commit-
always
I will
be
commit
the
ritual
wrong answer if you
seppuku.
don't include
I
it.
will commit ritual suicide. All right.
Execute Ethan.
Execute me. I forgot the start bit. It's game over.
Yeah.
Yeah, but yeah, don't forget the start bit. Don't make that mistake. You'll look like a fool. You'll look like an absolute fool. All right. The answer is 12. C. How long does it take in seconds to transfer the character from above, assuming the devices are configured at for 57,600 bits per second? So what do you
Divided by
do?
12?
You divide 12,
Yep.
you take 12 and divide it by your bits per second value, which will spit out 0.208 milliseconds. So that's also, units. Tell you this, if you divide 57,000 by 12, that ain't gonna spit out the right number. So
Yeah.
think about it that way.
It'll
So-
be in what? It'll be in frequency.
No, it doesn't even matter. The unit will be, I mean, yeah.
It'll
the
be
unit
1
will
over
be-
second. It'll be 1.
Yeah, the
it'll
unit
be
will be, I
hertz.
mean.
So
the unit will be, yeah,
just
it'll be
keep your
bad.
units straight and you'll be fine
Yeah,
on these.
So the
units.
answer is 2 microseconds. 2
Nah,
milliseconds.
it's
2 milliseconds?
it's 0.208 milliseconds. So 0.2 milliseconds. But
2
there's,
milliseconds.
but
Okay.
it's actually 0.208 all the way down, like three down, because there's that 8 is significant.
Yeah.
At that time scale, anything, it's always going to be significant. Like, until you move down into like the femtosecond range, no one cares about what happens at that speed. Because it doesn't. D, what happens when a new character is received in the receive buffer before the previous one is read by software? You shove
lost
the,
it.
yeah, you lose a character, but it will tell you that you'll set a buffer overrun error bit will be set. Now, the thing is, I could shove 1 million bits by some miracle, and it would only set that flag once. So there's no way to know how many bits you've lost. All it's going to tell you is that whatever you received ain't what you wanted. So you should probably resend the message.
Mhm.
So basically you can go handle that shit later. So what he says is the original character is lost, but the buffer overrun error condition bit is set. The error conditions may be investigated in the program. But all you need to say is that you lose it, but you set flag basically. All right. And it says, what does this interrupt service routine do? So we have a pragma vector. I use this ISR. Let's go.
So it's a receive vector. So
Oh,
whenever anything's received, it's
baby.
triggered.
Oh, baby. Let's go. All right. So that's literally it. In my final project, I had to figure this thing out because the only way we were used to doing it. And look, he still does polling. Cringe. Oh well. So it just polls. You go in and then it gets stuck in that while loop until there's actually something
Transmit's
there.
free.
Until the transmit's there, and then it'll just, oh, that's an echo, isn't it?
It's an echo. Yep.
Yeah, okay, that's an echo, and that's what he says is an echo. Yeah, no, but that let me tell you, that receive vector right there, I had to dig to find that thing because we only ever used polling for UART, and polling is cringe.
That's a lie.
No,
So
I looked
all
maybe
around.
that
you
he's
did,
doing, so
but-
all the interrupt service is doing is just creating the echo.
Yeah, look, because it comes, I mean,
Yeah.
this is just the ISR, and then this is the code, these 2 lines. So while IFG2, so while not IFG, so it'll sit at this while loop until it receives an interrupt flag from the transmit buffer, therefore saying it's free, right? And then it'll say, hey, it'll write whatever it received, which got you in here in the first place. So this is already populated, right? It'll just send that
Right.
into the transmit buffer, which is then, of course, sent out.
So it's like you hit a character on your keyboard and then it puts it out in the terminal for you.
Yeah, if I hit, yeah, that's literally it.
So that's a way of showing you in your hyperterminal what you're typing, basically.
Yeah, that's all it does.
Okay, but you highlighted, scroll back down a little bit. You highlighted the vector, the UCI, AB, yeah. So you knew that, like, was that a hint prior to you looking at the code or something?
No, I mean, it just says, what does this
Oh.
ISR do? So here's the thing. If
Okay,
you
cool.
don't understand this, you're gonna have a problem because you won't know that it's, I mean, you might still be able to guess what happens by just investigating the code line here. But if you don't know what situation gets you into the interrupt in the first place, you might not successfully guess that it's an echo.
The
But
key characters you want to look out for is RX and TX.
yeah, and
Yeah,
this is
right.
the,
RX
T
will
is
be
the
received,
transmit,
TX
RX
is
is received, yeah.
Yeah.
yeah, and this is the UCI RX buffer here, or RX
And
vector.
pretty much whatever he throws at you, because he could do one that's like, I don't know, UART A0 or B0. And as long as it's RX buff, TX buff, you kind of know what's going on.
That's all.
Right.
So this once you hit, like, this is how it worked in my program. If at any time
Every time I see that wow, I always assume that it's waiting on something, right?
it
Yeah,
is,
pretty
it
much,
is,
yeah.
but this is literally polling. That's what this line, these two lines is. It's an interrupt routine that then polls. But it won't be here long, ideally, because once
Well,
you,
you have to poll because you have to pause. Because if you threw in your receive,
I didn't need
character.
to. I was a magician. I didn't need to poll in my receive
Okay,
buffer.
okay.
No, I just don't. But the thing is, luckily here, this actually wouldn't be that big a whoop, right? Because let's say all the rest of the program does is transmit stuff. Well, the second you enter this, everything else stops. So this will open up real quick. It'll just prevent you from overwriting the transmit buffer.
Yeah.
So that's good. But even so, now on to F, which is two devices C and D are communicating using SPI. How many signals need to be routed between the devices? So let's remember here. SPI is not UART. It is not asynchronous. It means that there's going to have to be at least one more line than previously mentioned in the last instance, because this is going to need a common clock link. So that's a line. You're going to need a transmit link. That's a line.
You need a receive link.
Going to need a receive link. That's a line.
And SPI also has this nifty little feature called multiple slaves.
Well, yeah, slave select enable.
Yep. So you'll have to have a line to select which like slave device you're selecting.
Yeah, so that's kind of like,
talking to.
when I think of that, I think of it as like a letter with an address. So you can use slave select to interface a master with various slaves. But if you don't want every message to go to every slave, you use the slave select line to decide which slave to go to.
Yeah. And then the direction of like transmit and receive, it's not
It's master
TX
out,
and
slave
RX.
in, and master in, slave out. So that's MOSI and MISO.
MOSI, MISO, MOSI, something like that.
I mean,
you can interchange the characters
yeah.
basically.
But yeah, and so in this instance, the answer here, it says sketch the connection. He didn't do that, and we obviously won't do it.
Yeah.
But even so, a 3 or 4, depending on setting, is his answer, and that's because slave select is optional. So you don't have to use it, but you're gonna have to mention that it exists. So there's that one. And then G is two devices E and F are communicating using a parallel bidirectional link with 8 data lines. Half duplex, i.e. E and F cannot send data at the same time. In addition to data lines, what other control signals are needed to implement proper data communication? And he says sketch connections again. Well, he says 8 data lines. That's the only information we have so far, right?
So ENF cannot send data at the same time.
He basically says handshaking signals, 4 in total. That's his plan. That's his play here. Because it's in addition to data lines, which is 8 data lines, right?
Yeah.
So he needs an E2 FRDY and an ACY and an ACK.
I don't know if we'll have one like this.
I don't remember this communication protocol. I think it was like
no, we haven't gone over this, but he's trying to get it like make you think. The problem is we haven't gone over handshaking.
We might not have gone over. I mean, like he might have done it in the past, but he stopped because this is a final from 9 years ago. It happens.
Oh, 2002. It says.
What?
Yeah, it says 2002 on the file name.
There's no way. Nah, 2012. Eat shit.
Oh, okay, okay. It's just mislabeled.
It says 2012 at the top.
Yeah, what did he draw? He said there's like a ready and then there's an acknowledge. Something like that.
Yeah, he basically just says 8 data lines, and then he says handshaking signals 4 in total.
I mean, it kind of makes sense though, because it's a little bit like UART in that you have to have a header byte and a
Yeah.
stop.
Well, basically you need
have to have
he
start
has a
and stop
line
things.
for both device E, and so E to F ready. He has an E to F ready line. He has an F to E like busy line, an
Acknowledge.
F to E or like acknowledge. He's got an F to E ready line, and he's got an F to E acknowledge. But you said F to
Oh,
E
so there's
acknowledge
actually 4
twice.
additional ones.
Yeah, there's 4, so there's 12 in
Oh,
total.
lovely.
But he messed one of those up. It should be E to F acknowledge, but oh well. H down here. This is literally like it, because this is a bonus. This thing. So he says, what needs to be done to, okay, well, this is like using the bidirectional link and initializing it. This will not occur on our exam. That will not happen.
It could be a bonus. Could be.
It's not a bonus. This is the bonus. The DMA. Let's go.
Oh.
DMA will show up. DMA's poggers.
Oh no.
I mean, just memorize it. It's true. The DMA can be initialized to perform a transfer of block data from one place to another. It can send a whole ass chunk. That's true. List the DMA control registers. There are 4 of them. You have DMA XSA, which is your source address, DMA XDA, which the X's are just numbers. There's several versions of both of these. DA is destination address register. DMA XSZ registers your size. So that's like block, page, what have you, right? How much are you sending in one go? And then your last register is the CTRL DMAX control register, which is just, it's a control register. It's just turn it on, off, enable, set kind of thing. Then it says, could you use a DMA to transfer 128 samples coming from ADC12 controller to a buffer and RAM memory?
Probably.
If yes, explain what steps. So yeah, the DMA should be able to handle that because you just have the DMA source address be the ADC12 buffer, the DMA destination address be the mem buffer, and the DMA size is 128 word transfer. It can handle that.
Use illustrations. How would you know when the task has been completed? Whenever one of the bits in the control register,
it generates an
How
interrupt.
would
It
you
generates
know?
an interrupt when it's done.
Oh, really? Okay.
Yeah. And then it says what segments need to be on to display 5 digits on an LCD display. Digit 5,
0
a
through
digit 5,
4?
a digit 5, which should be so here's the thing, segments are labeled with letters. So ACDFG, because it goes ACD. You gotta look up a whole thing. It's a bonus question for a reason. You would just memorize the data sheet. Segment labeling. But I know that because that segment labeling is identical to that of a 7-segment display, which is exactly how the LCD works for segments. So that's how that be. So that's that one. Now there is another final, which is, as you can see, has the same.
Is this a later or earlier one?
December. It's the fall. They're in the same year.
It's the fall. Okay.
We've done that. We did all these interrupt stuff.
What are the chances I have?
We did assume that an ISR takes, so this is like low power mode processing. Now I have another study session going on in about 30 minutes for another class. So I'll probably end this one here, but I recommend everyone go back because this type of question, we've done this in homework and I could definitely see this occurring. The status lines and everything. But the answer key and this are also in his stuff, so I recommend going over it. It still is on Wednesday, so there's time to go through stuff. This is just another arbitrary signal thing. So look here, you can see we have a new signal. Right, funny monkey signal. Same kind of thing, 12-bit, right? Fun. More stuff. Anything very particularly interesting?
Doesn't absolute value like double the frequency of the function?
No, it just makes it all positive, so you don't have to send it up. don't have to
You
reference
know,
it.
Ethan, if time permits, you should consider, holding another study session before the exam on Wednesday. You should think about it. Think about it.
I might, because I have a
Yeah, that would be
final.
good.
I have a final exam tomorrow, but that's ISC 321, which is a meme class. I have 308 and 382 on Tuesday, which is why I won't be doing anything tomorrow after that midterm besides 308 and 382. And then obviously after that, I only have, I can probably push one in Tuesday evening, just to go over another final. Because this is
That would
good.
sound
Like the
lovely.
schematic switches and stuff is important to understand. Even though, yeah, this is important to understand. Some more, look, more DMA LCD bonus. Another bidirectional link, which definitely not happening for us.
November 29th, 2010. I have an exam from November 29th.
Yeah,
2010.
so there's that. All right. I'll end this one here and post it, and I'll update if I'll hold another one for the other final. Although it looks almost identical, except for like problem 4, I think. But yeah, that's the case there. So remember, in our infinite wisdom, we convinced Milenkovic to stay in person in the classroom during the exam. So anyone in Milenkovic's section is able to come into the school and sit in our normal classroom in Morton to take the exam. Now, what are the benefits of this? Well, first thing, if you have a potentially shitty internet at home, that room's pretty stable. That's good. Another thing, so here's what I like. I hate Respondus, and I don't like that it records me and such, so I'd rather just have it record me in a classroom. And also, the implicit assumption for any potential, things that occur during your test, whether it be someone bursting into the room, or every time you look a little too hard at the paper and the computer yells at you because you're not looking at the screen, right? Anytime that occurs, it's another flag during your Respondus thing where they'll be like, oh, he might be cheating. Well, if you're sitting in the room with the professor staring at you because he has nothing better to do because he's trapped in the room with us, you're pretty insulated from any accusations of cheating. So good thing to consider. So good moves. All right, that's
Thanks so
that.
much. Yeah.
Yep. Sydney, you want to just immediately go to the other one? Because
I am. Unfortunately, I have to attend that one too.
Let's go. All right. See you, gentlemen. Gamers.
Thank you. Thank you, Ethan. Bye-bye.
Adios.